All right, we'll go ahead and begin, and then so far what we've done is so last week we talked about how when we do Monte Carlo methods, the idea is instead of doing math to get our answers, we try to generate values from a distribution. So we'll try to get random values from some kind of distribution, and based on the values we get, we can get estimates for what we want. So we learned the inverse transform method, and we also covered rejection sampling. And these were just kind of two methods that we could use to get values from a target probability distribution. This week we're going to cover some more methods on generating values from target distributions, and today we'll look at some composition methods. Specifically, we'll look at the Box-Muller transform. Okay, and so the Box-Muller transform is a method to generate values from the normal distribution. Okay, so on Friday we looked at rejection sampling as a way to get values from the normal distribution. It was half of the normal distribution, but you can make the full normal distribution by then randomly flipping a coin and saying with 50% probability whether that number is going to be positive or negative, and then you'll get the full normal distribution. Today we'll take a look at the Box-Muller transform, which is how we can get values from the normal distribution. Now, normally I would probably write out all the equations and the notes, but when I tried that last time, it took a long time, and so it's much faster to just have these all prepared. I'm not a huge fan, I shouldn't say I'm not a huge fan, just my teaching style generally doesn't use lecture slides in general, but here's some lecture slides. These are prepared by Professor Tsang, and so he's gracious to let me use them, and so we'll take a look at the Box-Muller transform. This is a method for us to generate random normal values. The computer doesn't use the Box-Muller transform, okay? The computer uses inverse CDF, and even though there is not a closed form solution to getting the CDF of the normal distribution, it has a very good approximation formula that's like precise up to 16 decimal places, and that's what it uses. But it's the when you type in p norm to get the CDF of the normal distribution in R, it's really just an approximation that's accurate up to 16 decimal places, okay? Which, for our purposes, is good enough, okay? And considering that floating point numbers are only precise up to around 17 decimal places, it's not that big of a deal, okay? But if you wanted exact values, they're not exact values, okay? The Box-Muller transform falls under a general category of compositions and I guess compositions, which is using the known relationships between distributions, and I imagine this was covered in 100B, by using the known relationships to generate random values. So for example, if you are able to generate values from the standard normal distribution, you can then easily get values from the chi-squared distribution by taking those standard normal values and squaring them, right? So if you square them, then you'll have values coming from a chi-squared distribution with 1 degree of freedom, and if you want m degrees of freedom, then you just add up m of these z squared numbers, right? Okay. F distributions is the ratio between two chi-squared values, okay? U comes from a chi-squared distribution with m degrees of freedom, and V comes from a chi-squared distribution with n degrees of freedom, and then you take the ratio between them and over their degrees of freedom. That's your F distribution. And then the t-distribution, takes a random value, and then you divide it by the square root of a random chi-squared value. So these are just some known compositions. There's a couple more in your textbook, okay? So in the textbook, there's a few more compositions that are there. Today we'll take a look at Box-Muller transform. It's kind of long and detailed, and then it feels unsatisfying to then know that it's not even used by the computer. But it was an important transformation, and maybe just for historical purposes, it's important enough to cover here. So I'll go ahead and full screen this. I think this will all fit. Okay. So basically, the idea is we take two random uniform values, and then we switch from regular xy Cartesian coordinates to polar coordinates, and then we're able to get values from the normal distribution. Two uniform values will become two normal distribution values, okay? And so what we want x and y. Our goal is to generate x and y coming from the normal distribution, the standard normal, okay? And so if they're independent, then the PDF of x and y combined is just going to be the product of the normal density for x and the normal density for y. Okay, so this is just standard normal density for x, standard normal density for y, and then you just combine the two and you get this, okay? Because they're independent. Okay, so this is going to be our target density. Is that good? I don't know if you guys are writing this down or just waiting for me to post the notes, which I will. So either way, okay? All right. Now, if we remember Cartesian coordinates x and y, okay, switching to polar coordinates r and theta, then the relationship is x is going to be equal to r cos theta and y is r sine theta. Okay, so polar coordinates, you graph everything as distance from the origin r, and then an angle from the your starting point. Okay. All right, and so we have to change from the domain of xy to the domain of r theta. Okay. And the change of variables is given by this. This is like the Jacobian. I don't know if you guys remember all of this stuff, right? So to execute a change of variables, you kind of take the ratio of these things, and this gives you the Jacobian, which is going to be the derivative of x with partial derivative of x with respect to r, partial derivative of x with respect to theta, partial derivative, all of this stuff, right? And so you have r cos theta and r sine theta for your x and your y, and then and when you do all of this, so r cos theta with respect to r, it just becomes cos theta, and r sine theta becomes sine theta, okay? And then r cos theta with respect to theta becomes negative r sine theta, and then r sine theta with respect to theta becomes r cos theta, okay? And then when you do the Jacobian, which is the determinant of this thing, you do this times this, and this times this, and then you get our cosine squared plus sine squared relationship, and it just ends up being r, which is nice, okay? So then when we swap it out, okay, so we just replace the x and the y with r cos theta and r sine theta, which is how we get r squared here, okay, because it's x squared plus y squared, so that's going to become r squared. And then because of the change of variables, you include this term, which is just r, and so the whole thing becomes, this is the joint PDF with respect to where you've replaced x and y with r cos theta and y with r sine theta, and then and using the change of variables, kind of the derivative relation, the dx dy becomes r dr d theta. Okay, and then furthermore, we can do apply another change of variables where we're going to switch from r to r squared. Okay, and so dr squared will become 2r dr d theta. I mean dr squared. If we're switching from r to r squared, dr squared is 2r dr. Okay, and so this part right here, this r dr, will be replaced with 1/2 dr squared. Okay, so all of this, we're switching from r to r squared, so r dr becomes 1/2 dr squared. Okay, we leave the joint density part is here. Okay, the r dr becomes 1/2 dr squared, and then we can factor this apart. Okay, to this 1/2 e to the negative r squared over 2 dr squared, and then 1 over 2 pi d theta. Okay, and so this, and because we can factor these apart from r squared and factor apart the a function as with respect to r and a function with respect to theta, we can show that the values r squared and theta are independent because they can be factored apart into separate densities. Okay, so 1 over 2 pi, this would be the PDF of what? So we've factored the joint PDF. We factored the joint PDF of r and theta into two parts here. Okay, the PDF of theta is 1 over 2 pi. So that would be the PDF of what kind of distribution? Yeah. Uniform from 0 to 2 pi. Okay, which is exactly what we want, right? Because theta represents the angle, and so we want it to go from 0 to 2 pi, and every angle from 0 to 2 pi would be equally likely, okay? And then what about this? 1/2 e to the negative r squared over 2, okay? What if you just replaced r squared with some term x? So it's 1/2 e to the negative x over 2. Or 1/2 e to the negative 1/2 x. Does that look like a familiar PDF? An exponential distribution, right? With lambda 1/2, okay? Except instead of x, we've got an r squared term, right? So this is what we've got. We've got theta coming from the uniform from 0 to 2 pi, okay? And then we're going to let I guess instead of v x, we're going to let v equal r squared, and v just comes from exponential with lambda equal to 1/2. Okay, so if you just say this is, instead of r squared, you have v 1/2 e to the negative 1/2 times v. That's the PDF of the exponential with lambda equal to 1/2. And then over here, 1 over 2 pi. That's the PDF of the uniform distribution 0 to 2 pi. Is that okay? All right, and so now we know how to generate values from the uniform, okay? We're going to assume we can always generate values from 0 to 1, okay? And then so to generate values from 0 to 2 pi, you just take that value and multiply it by 2 pi. And then we'll generate a value v from the exponential with lambda equal to 1/2, which is easy enough for us also. Okay, using inverse transform method, we can generate values from the exponential distribution. And so we'll get a random value v, and then we will generate r by taking the square root of v. And then we get r cosine theta and r sine theta. So our values theta and r come from here, and that will give us x and y, which come from a standard normal distribution. What's going on here? Having issues. Okay. So anyway, we have this, and then again, using inverse transform method or inverse CDF method, getting values from the exponential distribution is not difficult for us. Okay, let me go ahead and just kind of demonstrate this, coding it up. Okay, so I'm going to have like U1 and U2, and these are both going to be R unit values. So I'm going to just ask for 100,000 values there, okay? All right, so how would I get theta using inverse CDF method? What transformation do I apply to U1? So we're getting, this will be our only source of randomness, okay? R unif for 1 and R unif for U2, okay? So U1, I just multiply by 2 times pi, and so now theta will be random uniform values between 0 and 2 pi, right? Okay. And then I'll let v, using inverse transform method, I'm going to just take the log of u2, and I'll multiply it by -2, okay? So that will give me values from exponential distribution. All right. Are there any questions? Okay, so now I have values theta and v. Then we're going to get r by taking the square root of v. Okay. And then we'll compute x by doing r times cosine of theta, and then y will be r times sine of theta. Okay. And that's it. So our only source of randomness is the uniform distribution, R unif. I run it twice, and then we do the Box-Muller transform. Okay, and we'll get x and y. And x and y will now come from the standard normal distribution. Okay, and to kind of demonstrate this, let me just give you a histogram of x. So that looks That looks quite normal. I can increase the number of bins. Not bins. Breaks. No? Guess that's that. All right. Histogram of y. Breaks equals 30. That doesn't. Am I doing something wrong with histogram? Breaks equals. I gotta bump it up to 50. Okay. Yeah, there we go. That looks better. All right. Histogram of y, histogram of x. They look pretty normal, so that's a good thing. Okay. Yes, question. Yeah. So it's from the inverse CDF method. So, all right, let me. I don't know if I can do this right. So. I'm going to try to draw on the screen here, which is rather tricky, right? So if f of x is 1/2 e to the negative 1/2 x, okay, then the CDF of this is going to be e to the negative e to the 1/2 x, right? Because the derivative of this will be this, all right? And then so we set this equal to so we'll let this equal u, and then we'll solve for x, and so all right, I'm sorry. This is not correct. So when I take the integral of this, let me just back up here. Okay, so the integral is from 0 to x of 1/2 e to the negative 1/2 t dt. Okay, and so on one end we get negative e to the 1/2 x, and then plus 1, right? Because you evaluate it at x and at 0. Or is it plus 1/2? Hold on. Why can't I do my math right? Okay. And then, okay, so we set this equal to u. Hold on. E to the negative. I don't know why I'm having so much trouble here. 1/2 t evaluated at x and at 0, right? So, okay, yeah. Sorry, 1 minus e to the negative 1/2 x. All right, so I have this. We set this equal to u, and then we get 1 minus u is equal to e to the negative 1/2 x log of, being natural log, 1 minus u is equal to 1/2 x, and then we multiply it by 2. Okay. So anyway, it's because there's a 1/2 term up here, so it's just inverse transform method there. I don't know if that clears it up. Okay, so we multiply by -2, and then the distribution of 1 minus u is the same thing as the distribution of u. Okay, they're both random uniform. So anyway, so we have this. Okay, graphically, let me just kind of show you. So if I plot x and y, this is probably gonna this not work? Let's just do our first 1,000 values. Shoot. Okay, it's not it's not clear what's let me turn on aspect ratio here. Okay, so this is what when you take two random standard normal things and you plot this, this is what you get. All right, let me see if I can draw on this. Okay, and the idea is, okay, here I can just randomly choose kind of some angle between 0 and 2 pi. Okay, so every angle is equally likely. Okay, all values, all angles from 0 to 2 pi are equally likely. Okay, and so this is going to be kind of our distribution of theta. Okay, all values between 0 and 2 pi are equally likely. Okay, so that part is that part's good. All right, and that's the random uniform part. But then if we look at any one of these pieces here, okay, if we just take, let's say this is the angle we've chosen, what we see is that values closer to the origin are much more likely, and values out here are less likely. Okay, so if you take any one of these angles, right, or like right here, and you look at kind of the distribution of dots, what we find is that values near the origin are much more likely, and values as you drift away from the origin, they're less likely. And those, the distribution of the dots follow an exponential distribution, which looks like this. Okay, so this is, you know, near 0, lots of dots. And then fewer dots far away. Okay, and that's what we see. Lots of dots near the origin in this middle region, but as we go further away, we get fewer and fewer. Okay, and so if we set up kind of our coordinates this way and say, you know, pick an angle between 0 and 2 pi at random, every single angle equally likely, okay, then and it appears all of these angles are equally likely, that's for sure. And then we say, all right, then where do we want to plot this? This becomes our random variable r, okay, which is going to be based on the exponential distribution. Okay, and so this is what we end up having. I think Wikipedia actually has a nice picture. Box-Muller, Wikipedia. Let's see. Look at this. Okay, and again, I don't know if this is any better, but it's kind of the idea that every angle equally likely, and then within each thing. Okay, these dots right here, this square, this is if you not randomly, but if you evenly generate values from 0 to 1 and 0 to 1 for x and y, and here it's shaded each of these things, it kind of shows you where each of these dots get mapped to after the Box-Muller transform. Okay, so this is what it has. So values out here get mapped that way. Okay. All right. Anyway, so that's Box-Muller transform. Oh, here we've got the values to get the plot there. Okay. So now we are able to generate values from the standard normal distribution. We can do more tests. We can do QQ norm on X, okay, and my computer's having issues here. Oh, there it is. Okay, so that looks like a straight line for the normal distribution. It's just because I have 100,000 points, right? Okay, and then you can do like a Shapiro-Wilk test for X to see if, okay, it says I've got too many. So let's do Shapiro test for the first 5,000 values, okay? And it gives us, so when I ask for a Shapiro-Wilk normality test on the kind of first 5,000 values in our sample, it gives me a p-value of 0.87, which means I have no reason to doubt that our values come from a normal distribution. Okay. Okay. Yes, question.
I have kind of like a big picture question.
Sure.
So we learned like different ways to generate values from different distributions.
Yeah.
This one, inverse CDF, and the rejection sampling.
Yes.
When do we use what for what situation?
When do you use what for what? This is a good question. Okay, inverse CDF. So it's basically the guided rule of thumb is if you can do the math, do the math. All right, and when you can't do the math, then use the computer. All right, and so if you can do the math and not do Monte Carlo methods, that's the best, right? Like this class is like only if like all of your other methods fail, which happens a lot, okay? All right, inverse CDF, if you can do the math to use inverse CDF, do it, okay? Because it's good. But a lot of times the math to get the CDF and the math to get the inverse CDF is hard. And so then you're like, okay, I'm not smart enough to figure out the CDF and the inverse CDF. I got to figure something else, all right? Rejection sampling will work pretty much always. You do need to know the value of the PDF, though. I mean, you do need to be able to calculate the PDF, which later on we'll see may not always be the case. And we have other methods that can be done if you can't even calculate the PDF, right? So you say, I've got a target distribution, but I don't even know the PDF. Okay, well, that sucks, and we got to figure out something else we can do. Okay, this this transformation method, this is all of these methods really, using the relationships here and stuff. This is I guess if you have the computational power, then these methods are fine. Okay, so for example, in order to generate a chi-squared distribution with 10 degrees of freedom, you have to generate 10 random normal values and then square them all, and then you add them up, right? And that could take a long time. Okay, if you had to do it manually, that'd be terrible. But doing it with the computer is not too bad. So I guess you just try to think like, how much computational power do I have to use? And you can choose accordingly. So rejection sampling, depending on how good your proposals are and how often you're rejecting, you might waste a lot of computational power, okay? Because you reject a bunch of these values. Okay, we're at, if we're here and we can generate random normal values, can we generate, so these are random normal values from the standard normal. Can we generate values from any other random distribution? And the answer is yes. Just use a Z transformation. So, so if you have W coming from some other normal distribution, not centered at 0 and not with standard deviation 1, then just do a Z transformation, right? So the relationship between some variable W, if it's normally distributed, to get its Z-score, you subtract it from the mean, and then you divide that distance by the standard deviation. And then to go from a Z-score back to the original thing, you multiply by the standard deviation and you add back the mean. And that's all you have to do, okay? And so, and these are just some kind of proofs to show that the expected value is what you want and the variance is what you want, okay? So just apply a Z transformation. Convolutions, these are, again, kind of using the known relationship between variables. So you guys are doing your first homework assignment, right? That's due this Friday. Okay. So one of the things is I asked you to do inverse transform method or inverse CDF for the binomial. Okay. And you have to use inverse CDF for the binomial. Okay. Some of you will be tempted to do a convolution, but you'll lose points because the instructions say use inverse CDF for the binomial. Okay. And if you thought of this other method for doing the binomial distribution, it is valid, but it's not inverse CDF, which is what the exercise wanted you to do. Okay. And that is basically you use the definition of the binomial, and I don't know if you guys, some of you probably thought of this or tried to do this, which is you're going to just generate coin flips and then you add them together and you say this is how many heads I got, right? So for the binomial distribution, if you want a binomial random variable with parameters m and p, you just flip the coin m times, and you say the coin will land heads or will return a 1 with probability p, and will return a 0 with probability 1 minus p. Okay, and then you add them up, and then you'll have a binomial random variable. Totally valid. Okay, and with a computer, convolutions are not hard at all, and they're quick. Okay, it's the convolutions in general cost the computer more time, okay, but cost your brain less mathematical energy. Okay, so and I mean that's a trade-off with all of these things, right? Like, why do we like R and Python? Okay, because they're like slow computer languages, but it's easier for our brains, right? If you want computer speed, then use C, and then you got to think a little bit harder when you program. Same thing with these convolutions. You know, if we asked, give me a binomial random variable as the result of 100 coin flips, and you know, probability, you know, 0.6 or whatever for each coin flip, you've got to generate 100 uniform values 100 coin flip values first, and then you sum them up, and that's only going to give you one value from the binomial. Okay, and maybe that's fine, but it could take your computer a long time, right? So, for example, here, let me just kind of code this up. So this will be convolution approach for binomial. And so let's say we want binomial with m equal to 20 and p equal to 0.6, right? So this would just require us, so let's say we want n samples, we want n samples. We want a total of 1,000 values, okay? And so u will have to do our unif. We're going to do n times 20, okay? Because we're going to need 20 uniform values for each value we want, right? And then all right, you know what? Let's do a loop. Okay, this will make it even slower, just for funsies. Okay, so I'm going to say for I in 1 through n. Okay, what we're going to do is we're going to generate 20 random uniform values, and then we'll say h is going to be the result of u1 less than or equal to 0.6, right? So this will be true if our random uniforms are less than 0.6, and then what we will do, our results will just be, we're going to store into our results in position I the sum of h, okay? And this will give me 1,000 values from the binomial distribution with p equal to 0.6, right? So, right, so I'm just generating 20 random values. I'm going to see how many of those values are less than 0.6. H will be a true-false vector, and then I add those up. The ones that are less than 0.6 will be true. I add those up, and then I'll store those results. Okay. Okay, we're done. And let's just do, let's see the table of our results. Okay. And that seems pretty reasonable. Table of our results, and then let's divide that by 1,000. Okay, and then let's just see D binom 5 through 18 for size equal 20 and probability equal 0.6. Let's round this. Okay, so the theoretic values are 1% versus, and then the next for 6 is between 5. You know, we observed 3 times that the theoretic is 5%, okay? And there's pretty good match, okay? We're expecting 71% or 71, and we got 71. We expected 117, and we got 114. We expected 160, and we got 145. We expected 180, and we got 199, okay? So, you know, a little, not exactly the same, but pretty close, just between our binomes, right? If I did more than 1,000, I'd probably get even closer match. So these are empirical results. These are theoretic results. Yeah, I'd say we're getting pretty close. 160 versus 154, 180, 178, 166 and 166, 124, 124. So okay, so this is the convolution method where you're just using the definition of the distribution, okay, as a, kind of a sum of a bunch of random variables. So binomial would be the sum of Bernoulli's, and then Poisson would be the kind of the sum of different Poisson variables, right? And then, chi-squared distributions, the sum of chi-squared variables, and so on and so forth. Okay, the gamma distribution is a little bit, the beta distribution requires the use of the generation of two gamma variables and so on, okay? And I think I've got, in the next homework, some exercises here. Okay, so we'll end here, and then we'll see you guys later then.